Okay, so thanks for joining us for James' talk about breaking the bank care.
Thank you. Good morning, everyone. My name is James Wyke. I'm a senior threat researcher with Sophos, based in our UK headquarters in sunny Abingdon. This presentation is called Breaking the Banker, and it's about automated configuration data extraction for banking malware. So I'll begin with a brief introduction, talk a little bit about what's been happening with banking malware over the last couple of years, some of the good things, some of the bad things. And then I'll talk about what kind of information can we understand about banking malware, what kind of data can we extract, why that data is useful, and how we can go about actually extracting the data in the first place. I'll then talk about the system that we've built to basically automate this process. Talk a little bit about the architecture, some of the important stages, and then briefly show some of the output and the results that we're getting from the system. I'll then talk a little bit about some of the pitfalls and some of the problems that we've encountered during the development of this system so that we can share the knowledge that we've built up for anyone else who's thinking of developing a similar sort of system. And then I'll sum things up at the end. So over the last year, 2 years or so, there's been some really successful banking malware botnet takedowns. So Operation Tovar took down Gameover Zeus and was a huge operation with many different law enforcement departments from lots of different jurisdictions, from lots of different countries all over the world. Lots of security companies involved as well. A huge amount of resources, a huge amount of people, a huge amount of organization involved. But ultimately, it was pretty successful. That pretty much ended Gameover Zeus, which was one of the largest botnets, not yet alone banking malware botnets, that there's ever been. Also, the takedown of Shylock was very successful. Shylock was a banking malware family that had particular interest in the UK, some other European countries as well, but again, the network infrastructure was seized, and it was very successful, and we haven't seen Shylock reemerge since. But what we have seen since these kind of takedowns is for other banking malware families to emerge and take the place and fill the vacant space left behind. So families like Dridex, Dyreza, Vawtrak, various Zeus variants, particularly Kin's variants, they've all become more popular since these other families have been taken down. So banking malware, despite some really successful actions, it's not a problem that's going away. You cut off the Hydra's head, and two more emerge. So what can we do about it? Arresting people is a pretty good way to go about stopping them writing malware. Especially if you arrest the right people, the people at the top of the chain, the people who are actually writing the malware and making all the money out of it. That stops them from doing that, but it also acts as a very strong deterrent to stop other people doing the same thing. But arresting people is not an easy task, particularly when they live in jurisdictions and in countries that perhaps don't have extradition treaties, or they live under governments that are not cooperating with the process of trying to arrest them. So stopping short of arresting people, one of the things we can try and do is to understand the malware and to find out as much as we possibly can about it. Find out about how it's working, what the people using it are trying to do, and we can do things like track the campaigns, detect active compromises, and try and prevent future compromises as well. Try and make the banking malware effectively not as good at doing its job. So when we're talking about finding out about banking malware, I'm really talking about what kind of technical information can we extract about banking malware samples and the artifacts of execution when banking malware runs on an infected machine. So it's things like command and control addresses, so all of the command and control addresses as well, not just any addresses we might observe the malware communicating with, but backup command and control addresses as well. Cryptographic keys, so many of the other types of information that we want to extract will be encrypted or encoded in some way, and we need to extract the cryptographic key material that is necessary to decrypt that data. And things like campaign IDs and botnet names and build versions. This is all metadata which we can use to differentiate one sample from one banking malware family with another sample from the same banking malware family. So things like botnet names and project IDs and campaign IDs can tell us information about when the sample was in circulation and where it was targeted at. And build versions can tell us exactly which version of the malware we're dealing with. And things like domain generation algorithm seed values. So if the banking malware family that we're dealing with uses a DGA, typically these algorithms will take some sort of seed value which goes into the algorithm and will change the entire list of domains that are generated. Change the seed value and you get a completely different list of domains. So if we want to replicate the algorithm and pre-generate all the possible domains offline, see which ones are alive and proactively block them, we need to know what the DGA seed values are. And it's pretty common for banking malware families to have sort of traditional bot capabilities where a command and control server can issue a command to the infected machine. And so if that happens, we want to know what commands were issued, what the arguments to those commands were, because again, that can contain very useful information, and potentially the responses to those commands that the infected machine made as well. And downloaded configuration files. So again, pretty much every banking malware family during execution downloads a configuration file which contains data like web injects and URL redirects and URLs from which further modules could be downloaded. So these configuration files are full of extremely useful information, so that's the kind of data we want to extract as well. So once we've extracted this data, how can we use it? So we can do things like generate indicators of compromise. So host-based indicators of compromise, things like file names, registry key names, mutex names, process names, all pieces of data that we can use to flag up instances on a host where this malware has infected. And network-based indicators as well. So things like IP addresses, URLs, domain names, all pieces of data that we can use to highlight active infections from the network. And being security vendors, this kind of data is also the kind of thing that we can use to provide protection. So we can take this type of data, feed them back into our products, and actually protect our customers from this happening as well. And we can also use this data to tell us a lot of information about the kind of targets that the people behind the malware are aiming at. So especially when we're looking at configuration files, web injects, we can see which URLs are being targeted, which banks they're trying to steal data from. And if those organizations aren't in the financial sector, we can also see exactly which industry sector they're targeting. And we can also see which countries they're targeting as well. It's becoming increasingly common that particularly web inject packs will target banks and organizations in a specific country or a specific group of countries. So if we extract this data, we can see which countries they're trying to target. And another common feature of banking malware is to enable keystroke logging when certain processes are launched. So if we get that list of process names that they're targeting, again, that can tell us information about what kind of data they're trying to steal. So if we see things like point-of-sale software processes, enterprise resource management processes, again, that tells us, especially when it's something that's slightly out of the ordinary, can tell us a lot of information about what kind of data they're trying to target. And we can also use this data to tell us, so reveal the actions of what the malware did. So we can find out what commands were executed, and potentially we can use this data to tell us what data was stolen, what data was exfiltrated as well. So how do we go about getting this data? So the manual approach is we need to do some reverse engineering. We're going to debug, disassemble the sample, dump regions of memory, we'll dump data from the packet captures, we'll decode it, find the data we're interested in, and then we'll do the same thing with the next sample. So this is going to be slow the first time because we need to do the initial reverse engineering, but when we have to do a manual process for the next sample as well, again, it's going to be slow as well. It requires an analyst to do this every single time for every single sample. So obviously, we need to automate this process. If we want it to scale, we want this to be repeatable, it needs to be automated. The argument for that's very clear. We're still going to need some human input because we still need to do some reverse engineering. We need to write the code in the first place. But once we've done that, the system should take care of the rest of the samples for us. So obviously, we need to automate. How do we go about automating something like this? So I think there's a wide range of possible ways of automating something like this. There have been several presentations this week where other companies are doing similar sort of things in slightly different ways. So a couple of the options that we looked at is you can implement something like a crawler. So implement the client-side part of the command and control protocol, get a bunch of command and control addresses for the malware family, and reach out and download configuration files. A few possible stumbling blocks there are that we're going to need to feed the system with up-to-date data. We need to get new samples of our malware families, extract the command and control addresses, feed them into the crawler system so that it can continue to download live configuration data. And we're only really getting data that's been downloaded as well. So we're not really extracting information from a particular sample, and we're not necessarily going to find anything that we're not sort of expecting to find. So if sort of new samples do something slightly differently, our crawler's not going to know about it because we're just downloading configuration files. And another thing we have to be wary about with a system like that is if the bad guys start realizing that our system is a crawler and not a genuine infected machine. If they do that, they might just take simple steps like blacklisting us, but they can also get a bit more creative and start feeding us false dummy data that's designed to mislead, maybe designed to like induce false positive, or just maybe keep us sweet and not realize what they're doing. And sometimes it can be really difficult to work out when that's happening. So another possible solution, and one that we've gone for in the end, is we can embed this system into an existing sandbox system. So many security vendors and many companies that aren't security vendors have very large-scale sandbox system through which they're putting many thousands, many hundreds of thousands of samples every day. So if we can use this existing infrastructure, then there's lots of problems that we're going to need to solve that we don't have to solve anymore. They become the problem of the underlying system that we're using, which is most likely going to have a large team of people whose responsibility it is to maintain and to ensure that it continues to work and doesn't fall over. So we don't have to worry about those problems anymore, which is great. And because we're generally putting pretty much every sample we can through a system like this, we also don't have to worry about finding new samples of our malware families. They're already going through the system. Another nice thing about sandbox-type system is that one of the things they're geared towards is providing a report of on a per-sample basis. So submit a sample, see what it does, and again, this is the kind of thing we're going to want for configuration data extraction. We want to submit a sample to it and see what configuration data we can extract. So again, that's good for our purposes. And another feature of these kind of systems is that generally part of a larger sort of flow of data. So they're receiving data in the form of samples, they're doing work, and then the data that they're producing is generally being passed off to other systems. And again, that's exactly what we want to do with automated configuration data extraction. So our solution to banking malware, it's not really the solution to banking malware, but the system that we've built to try and help with this problem. So the sandbox is based on the Cuckoo open source sandbox, which is written in Python, which is a great framework, extremely nice to update, to modify, which is exactly what we want to do. So we've added a few things around things like enhanced data capture. We need to make sure that we've got as much data as possible so that we can extract this configuration data we're interested in. We've added some processing modules, which is the stage in Cuckoo where you take the data that's being captured and sort of analyze it and convert it into useful information. And that's where we do the actual configuration data extraction itself. And we have various reporting modules, which is where the data that's been handled by the processing modules goes on to the next stage, which formats it and presents it and can send it on to downstream systems. So this is a graphical overview. It's really a simplified overview of the Cuckoo architecture, really. So the job starts, the sample's executing, we're collecting data during analysis, and then once it's finished executing, we're collecting more data at the end of analysis. Once we've got all the raw data, it then goes on to the processing modules, which is where we do the configuration data extraction itself. And then it goes on to the Cuckoo reporting modules, which is where the data gets prepared and formatted, and then you can send it on to other systems. So we can send it on to things like a sample database system, a URL database system, and any other database or system where we think we can do useful things with the data that we've extracted. So just to highlight a couple of the sort of important stages of that then, the first one is when we're capturing the data. So again, we need to make sure that we've got all the raw data available to us for later stages. We want to make sure we're not throwing away anything that we might later want to use. So in terms of the memory, we need a full memory dump at the end of analysis, but it's also useful to capture data at certain stages during analysis as well, particularly when we've got things like a process starts and finishes before analysis ends. The memory space of that process is generally not going to be available at the end of analysis. So we add sort of an extra hook on exit process, so we'll dump the memory when the process ends, and in certain situations when memory is being freed as well. So we're looking to try and capture as much unpacked data as possible. On the network side of things, we want a full capture of all the network traffic in a PCAP file, again, which is something that Cuckoo already does for us. But several banking malware families communicate over encrypted channels as well, HTTPS, SSL, TLS. So we need to man in the middle of that so that we can get an unencrypted form of that traffic. In terms of the disk, there'll be certain files that we want to capture as well, but probably more importantly, the registry as well. It's quite common for banking malware to store, especially configuration data, in the registry. So we need to make sure we're lifting the hives off the disk so that we can analyze and process them at the end of analysis. It's also quite handy to have slightly unusual conditions for execution during analysis. So certain malware families, Vawtrak's a good example, a simple example where there won't be any communication with the command and control server until a browser process is launched and an outbound request is made. So it basically puts a hook on HTTP send request in a browser process. As soon as that hook gets triggered, it will then start looping through its beaconing process. So we need to make sure that those kind of conditions happen during analysis because we want to see that full interaction with the command and control server. So Cuckoo has a nice feature called analysis packages, which is where you can effectively set up those kind of slightly unusual conditions for execution. So once we've captured the data, we need to process it. And this is where the Cuckoo processing modules come in. So we have a configuration data processing module that every single job that goes through the sandbox will run through. So we need to filter it to only run against the specific malware families that we're going to do data extraction for. So once we've identified the family, we'll then instantiate a new Python class that will do the data extraction for this malware family. So a slightly, hopefully, clearer graphical view of that processing stage. So there are various Cuckoo processing modules, behavior processing, which analyzes the trace of events from the injected DLL, the network processing module, which deals with the network traffic, and then we have a configuration data processing module. We perform that filtering step, identify the specific family that we want to extract data for, and then we launch the new Python class that will do the data extraction. And then the remaining Cuckoo processing modules will run. So we need to implement one of these Python classes for each family that we want to perform data extraction for. So generally, these classes will do things like find certain data structures in the memory of dumped malware files, we'll extract the piece of code we're interested in, we'll decode it, take files from the disk, the registry, pieces of the network capture, decode the data, and then add it all to a Python dictionary, which gets passed on to the overall results dictionary for the analysis job, and then handed off to the next layer of cuckoo processing. Slightly more, a quick sort of example of one of the processing modules for Vawtrak, also known as NeverQuest, which is from the Gozi sort of dynasty of banking malware. So the filter stage for Vawtrak is just Yara signature against memory dumped files. Because we're dealing with files dumped from memory and not files from the disk, they're not packed, and generally it's quite easy to write these kind of signatures for. Vawtrak's a nice example because once you've dumped it from memory, it's full of easily identifiable strings. So we can write a nice, simple Yara signature for it. Once we've identified we're dealing with Vawtrak, we launch a new class called Vawtrak config. And so these classes inherit from a parent config data class, and we've got various sort of fields and helper functions, things like family name, the path to the analysis directory, which is where Cuckoo stores all the data that's been gathered during the analysis job. We then need to implement a get data routine, which is where we do all the actual extraction work, and then we return a dictionary of data at the end of the routine. So inside this get data routine for Vawtrak, we've got various methods, including get C2 addresses, which is where we're going to pull out the command and control servers. And that routine is basically just going to perform a regex for this block of code, because in there we have a pointer to the encrypted blob, which is where Vawtrak stores its command and control servers and a few other pieces of useful information. So we do a regex for that block of code, find out where the encrypted blob is, decode it, and then we've got that data. We've also got various other routines inside get data, things like get downloaded config, get received commands, get decoded modules, and these are all looking at the network capture and pulling out certain pieces of useful information from them. So one trick that we find quite handy when dealing, especially with HTTP data, is we convert the PCAP file to an HTML archive file, a HAR file, because when dealing with HTTP data, it's a bit easier to process. HAR file is JSON, requests and responses are grouped together, and it's slightly easier to deal with than a raw PCAP file. So once we've extracted all this data, we store it in a Python dictionary and return it back to the next layer of processing. So the next layer that comes in is the reporting modules. So these they take the data that's been collected during analysis and what we've processed, and we've extracted our configuration data, and the reporting modules present it to other systems. So one of the reporting modules that's already in Cuckoo basically generates a web-based report of all the results of the analysis. So it takes the data, stores it in a Mongo database, and there's a nice Django-based web interface into the results. So we can use this existing reporting module to generate a per sample report for a human on all the data extracted for this particular sample. And then we have various other reporting modules that take elements of the data we've extracted and pass them on to other systems to be actioned on. So things like URLs, domain names, and IP addresses, we'll send them on to a network reputation system. If we've managed to decode PE files from the network capture, from the registry, from anywhere else, we can then send those PE files onto a sample processing system. And they may get fed back into the sandbox system, or there may be automated detection added for them, and that kind of thing. If we've extracted web injects, and if we've managed to decode any downloaded configuration files, again, we can send that data on to another system. So a few quick examples of portions of some of the data that we're extracting for various malware families. So this one is Citadel. So you can see we've got the command and control addresses, we've got the family name, a specific variant of Citadel we're dealing with, and various items of key material we're going to need to decode the network traffic. And you can also use those kind of key, like the RC4 key, for example, is quite an interesting way to track samples as well. When the malware guys reuse the RC4 key, it might mean that it's the same guy. Dyreza example, so again, we've got all the command and control addresses, and we've got the campaign ID in this example. So Dyreza campaign IDs tell us some useful information about when the sample was sent out and where it was targeting as well. So this is 2506 UK 12. It was on the 25th of June, and it was targeting the UK. A Vawtrak example. So again, we've got all the command and control addresses, and we've got various items of metadata that's interesting about Vawtrak samples. So we've got the specific build version, we've got the project ID, which can tell us about where it's targeted at, and we've got things like the format string, which is used to generate the post request that Vawtrak will use to communicate with its command and control servers. And we've got to check some of the public key, which is used to verify updates and configuration data by Vawtrak. So we can see if that public key ever changes, for example, which is quite interesting because with Vawtrak, that doesn't change, which also tells you some sort of information about the botnet. I mean, that implies that there's one entity that is pushing all the updates and is signing all the data that's being verified with that key. A web inject example, so if you can see that from the back, we've got the specific URL that this code will be injected into, where in the page it will be injected, and the actual code itself that's going to be injected into the page. When it comes to extending this, adding new malware families, it's a relatively painless process. So we need to add a new filtering stage, which is generally just adding a new Yara signature, and then we need to implement a new Python class to extract data for this particular sample. Because this is relatively painless and it shouldn't take too long to actually code this part of it, we don't need to update the framework or do anything complicated like that. It means we've got plenty of time to focus on the bit which does take time, the reverse engineering part. So some of the pitfalls that we've encountered. So execution conditions is something I mentioned before. So we can use cuckoo analysis packages to make sure that the right conditions are there during execution to see the fullest extent of the sample's interaction with the command and control server and just see as much as possible about what it's going to do. But the length of the analysis is another thing which can be important to keep in mind, particularly families that use domain generation algorithms. Timber is quite a good example. It can cycle through a very large number of domains, and it might be some time before we generate a domain that's actually live. So we need to make sure that the analysis goes on long enough that we generate a live domain and we can see some interaction with that server. Geo-targeting is another thing to be wary of. So it's an increasing trend that on the server side, some banking malware families will deliver a different configuration file based on the country that the victim is connecting from. So there's a geo-IP lookup of the victim's IP address, and if they're in the UK, they'll get a configuration file with web injects targeting UK banks. If you're in the US, it'll be targeting US banks, and so on around the world. So if your sandbox or whatever other system you're using to gather these configuration files is always connecting through one IP address in one country, you might only ever see data that's targeting banks and organizations in that country. So if you want to get full coverage of all the possible configuration files you might see, you need to have multiple exit points in as many different countries as possible, as many different regions as possible, and cycle through them, or try the same sample from different exit IP addresses and see if you're getting different data back. Platform coverage is another thing to be wary of. Dridex is a good example where it has an x86 downloader, but if you're running under x64, it will download an x64 version of the main DLL. Under x86, it'll download an x86 version. So if the system you're running under is only x86, you're never going to see the x64 version of the files. So it's important to have as wide a platform coverage as possible. So summing up then. So we've got a system which is doing automated configuration data extraction. We're extracting that data in a human-readable form in terms of the web report that we're generating, but probably more importantly, a machine-readable form as well. So certain portions of that data are being handed off to other systems to be actioned on, and that's really where the protection aspect comes in. We can provide immediate protection against those artifacts as soon as they've been extracted. And it's relatively simple to extend. We can add new malware families without having to update the larger framework. We can just focus on the specific part of the malware, the payload part, if you like, and not have to copy and paste and re-implement anything. And because we're using an existing sandbox framework, which hopefully scales, and we could be putting 500,000 samples through it a day, we're now potentially extracting data from 500,000 samples as well. There's a whole team managing this system and resourcing the system as well. So we benefit from those kind of things that the underlying sandbox system has. And ultimately, the kind of data that we're extracting, we're seeing a positive benefit in terms of the protection that we're providing to our customers. And that is it.
Okay, thanks for your presentation. Unfortunately, we won't have any time for questions, so if you have any specific question for James, please ask him directly later today or at the bar later tonight.